Okay, hi everyone again. In this video, we're going to go over two dependent samples or matched pairs. So in the last videos, I went over independent samples and testing the difference of two means and difference of two proportions for independent samples, but here we're going to go over dependent samples. So first of all, let's go over the definition. What is a matched pair design? First of all, a matched pair design is an experimental design. We know we had observational designs and we have experimental design. Experimental, that means you do an experiment, you treat the sample to something and then you kind of want to see what happens to the sample, measure the changes. Subject can be grouped into pairs. The selected pairs are related in some way. So example, the person before and after a treatment. So this is basically what we're going to go over in this lecture, and most problems are before and after. What is a treatment? Examples of treatment, it could be tutoring. We want to know how effective tutoring is for students. Taking a course, so we want to know what happens before and after the course, if the course is effective or students learn in that course. Sports training, taking a medicine, or weight loss programs. So all these are treatments and these are experimental designs. So you have the sample, or even if we talk about one person, the person before and after the treatment. So that's what we're going to be testing in this lecture. Now I put a note, it would be also other types of pairs, but this lecture will concentrate on before and after treatments. What's the goal? With some level of significance, we want to know if the treatment is effective or has an effect. So these are keywords we have to be careful when we choose our claims. So effective, that means it has a positive effect. Has an effect means it can have a negative effect or positive effect for all subjects. For one person, it's easy to know. For a sample, we can always calculate that. But for the population or all subjects, what we have to do is we have to do the hypothesis testing. Now, match pair t-test for difference of two means. So I put here t-test because it is a sample t-test and you know about t-test from the last lectures. And we're going to go over the steps, but there are some requirements. The samples are dependent, so or we call them match pair. That's number one. The match pairs are simple random samples. N has to be greater than 30, or the differences are from a population having approximately normal distribution. In our problems, these requirements are satisfied. So unless if you just get a problem and then the problem is going to say, see if the requirements are satisfied. But all the match pair problems in this section or in this lecture is going to be, we assume that they're all satisfied. Now let's go over the steps. The steps are just hypothesis testing steps. Step number one, we have to identify the hypothesis or just write the claim as we went over this. There are three types of claims. One is HO mu sub d equals to 0, H1 mu sub d is not equal to 0. So this is a two-tailed test. I will let you know what mu sub d is in a second. So you can have two-tailed test or right-tailed test or left-tailed test, just like before. And HO, you put all of them equal to 0. Then we have to calculate the critical values. This is a t-test, and the critical values are just t-values. You can use the table, but the best way to use your calculator, as we learned, it's inverse T. You put the area and degrees of freedom, and the degrees of freedom are n minus 1. Test statistics. We know test statistics is a formula. So for match pairs is d bar minus mu sub d over s sub d divided by square root of n. Mu sub d is always 0 because it's assumed in HO. Now let's go over this. D stands for difference. 1D is the individual difference. When you calculate the difference, you do before minus after. For example, if an individual takes a class, that the professor can give that individual a final test the first day of the class and a final test the last day of the class, and just check the difference. So the professor can take the score of the first day, which is before, minus the score of the last day, which is after. And it's always before minus after. That difference can be negative or positive depending on the situation. D bar is called the mean of the differences for the sample. Now we talked about one individual, but when we have a sample, we don't have only one individual. We have uh, several individuals. So 5 people, 10 people, 20 people, 30 people. So one by one, you calculate the differences for each individual. Then you take the average of that. That's called D bar. It's like X bar, and it's the same formula, sum of these over N. Mu sub D is the mean of the differences for the population. That's what we're going to be testing. And you saw that in the claims, that's what we're testing. So then we have S sub D. S sub D is the standard deviation of the differences. S sub D, we have the formula square root of n times sum of d squared minus sum of the quantity squared divided by n times n minus 1. However, I put a note here for you to find D bar and SD. You can use your calculator. So you can go to stat calc and then just pick 1 bar stats. D bar is the same thing as X bar in the calculator, and S sub D is the same as S sub X in the calculator. And N, wherever you see N, we already know N is the sample size. So always. Then once you find the test statistics and you have the critical value, you have to make the conclusion. Same way, if the test statistics falls in the shaded area or p-value is less than alpha, so you reject HO. I just put a little example for you, and we have gone over this. I'm sure you already know this. If the test statistics is in the shaded region or p-value is less than alpha, it's alpha, then you say reject HO. If the test statistics falls in the non-shaded area or p-value is greater than alpha, just like here, non-shaded area is right here. Again, the pink area is the p-value, or the p-value is less than alpha, which is right here, then you fail to reject HO. Finally, we make the final conclusion. In this type of testing, we just say at the end, if the treatment is effective or has an effect, see if you have enough evidence to support that, or the treatment has no effect or it's not effective. Then there is one little point to know also. We can find the confidence interval for mu sub d. So mu sub d is a number between d bar minus e and d bar plus e, is exactly like mu. And we did x bar minus e and x bar plus e. It works exactly the same thing. The critical values are t values, and the margin of error is t sub alpha over 2 times s sub d divided by square root of n. And again, the degrees of freedom are n minus 1. It's a very good idea to see an example and see how all this work, and I can show you the calculator also. So if it says use the traditional method of hypothesis testing. The traditional method is only when you find the test statistics and you compare the test statistics to the critical value, shaded area or non-shaded area. To test a claim about the means of two populations, assume that two dependent samples have been randomly selected from normally distributed populations. So these are the requirements that I put for you in the beginning, and it's assumed that they're satisfied. Let's see what the problem says. 5 students took a math test before and after tutoring. Basically, this is the treatment. Their scores are as follows. So we have the scores in this table. Using 0.05 significance level test, the claim that the tutoring has an effect. You have to read this very carefully. Here it says has an effect on the math scores. So if we go here, I found these here. So we have for the first student, the before test score is 77 and the after is 81. So D is before minus after, you get -4. Basically, this student improved. So the score D is negative. In this case, if D is negative, it has a positive effect. Second one also, if you do, you get -9. So, and we see the scores has improved. So for that student, third student 66 minus 64 is positive 2, and that has a negative effect, and so on. The last two, they both are negative. In this case, if the difference is negative, then it has a positive effect. But the problem says just check to see if it has an effect. So it's not talking about positive, or it doesn't say if it's effective or it's not effective, just has an effect. Step number 2, we can find D bar and SC. We can use our calculators again. Enter all those differences in L1 and go to one bar stats. You find D bar, which is the same thing as X bar in the calculator, is -5.2, and S sub D, which is S sub X in the calculator, and that's 5.45. Now, writing the claim, we have to be very careful which one we are going to choose. So let me go back to those claims. We have to choose one of these claims. By reading the problem says if the tutoring has an effect. So we're not looking for a positive effect or negative effect. Has an effect, that means mu sub d, as long as mu sub d is not equal to 0, and we can prove that, then we have enough evidence to say that it has an effect. So we don't pick these two. That's the claim when the question says has an effect. Let's go back to the problem. So we write the claim, and you don't have to put OCCC in this case if the tutoring has an effect. So I put effect here because mu sub d is not equal to 0 and has no effect if mu sub d equals to 0. So next we have to find the critical values. This is a t-test and it's two-tailed. For two-tailed, we always divide alpha by 2, so we get 0.05. Use your calculator, inverse the 0.05. Degrees of freedom is 5 minus 1, which is 4, and you get -4.604. And this one is positive 4.604. Degrees of freedom, I put it here for you. Next step is the test statistics. D bar minus mu sub d over S sub d over square root of n. We have D bar, we calculated that -0. This is always 0 over the standard deviation over square root of n. And if you do that, you get negative 2.13. Negative 2.13 is in the non-shaded area. First conclusion, failed to reject HO. So you come here, if we fail to reject, that means we accept HO and we reject H1. Then take a look at that. We accept the claim that says no effect. So we don't have enough evidence to say that tutoring has an effect for all students. Although it did have an effect for the sample or for each single individual, but on the long run for the population, it doesn't, we don't have enough evidence to say that it will have an effect for the entire population. And again, with the significance level of 0.01. The second example, I put an example here. Oh, what we can do, let me show you the calculator with this. I think it's a good idea for you to see how the calculator works. So let me stop sharing this and let's share the calculator screen. So let me clear that. So again, the first thing you do, you go to stat, edit, and let me clear these lists. And you put the differences. And I do have them here, so let me enter those differences. So we had, don't forget the negative sign. So the first one is negative 4. You enter it, then we have negative 9. You can enter that, then it's 2. Then it's negative 3. Then it's negative 12. So these are the differences. Then you go to stat. And again, if you want to calculate D bar and S sub D, let me show that to you. You can go just to one bar stats. Frequency list, we don't need it here because it's only one list. Calculate. And here is D bar negative 5.2. And we have S sub X, which is S sub D, which is 5.45 approximately. Now, if you want to test the claim, you can go to stat, test, and this is just a t-test. So take that. Let's pick stats here because we calculated mu sub d. Not mu sub d, but d bar and s sub d. Mu 0 is in the claim, and that's 0 in this case. That's mu sub d. X bar 5.2, we have it. The calculator has it. Standard deviation 5.45, it's there. N is 5, and we pick the test that says it's not equal to. And all you have to do, just calculate. Negative 2.13, so the calculator gives you the test statistics and you have the p-value also, and these two, x bar and s sub x, it's there too. Now if you go to stats and you go to test, again pick t-test, that's second way of doing it. We know all our differences are in L1, so you can pick data if you want. And list is L1 because we did enter all the differences in L1 and the claim is good, and you can just say calculate and you get the same answer. So if you input the differences in L1, then you can go directly to data and then do it without needing to calculate X bar or S sub X or D bar or S sub D. Okay, let me stop sharing this and let's go back to the next example. Now, this example is a confidence interval example. It says construct confidence interval for mu sub d. The mean of the differences d for the population of paired data. Assume that the population of paired differences is normally distributed. So we have the formula. I put it for you on the top. So d bar minus c mu sub d, and it's d bar plus c. E is T sub alpha over 2 times S sub D divided by square root of N. Again, 99% confidence, that means this middle area is 0.99. The area in each tail is 1 minus 0.99 divided by 2. You can do inverse T 0.005 from here. Degrees of freedom is 8 minus 1 because N is 8. And it's 7, and you get that number. You can calculate the margin of error 3.499 times 2.911, which is S sub D divided by square root of 8, which is square root of N, and you get 3.601. Writing the interval, it's D bar minus E less than mu sub D less than D bar plus E. D bar is 3.125 minus 3.6 less than mu sub D and less than 3.125 plus 3.601. So the answer is negative 4.76 mu sub d and less than 6.726. And if we go back to the problem, we see that B is the answer. You can use your calculators by going to stat test, and in this case is T interval. And let me go ahead and do that for you. So we can go to stat test and scroll down to T interval. And here it's stats because stats are given. So our X bar is D bar in the problem, which was 3.125. And S sub X is S sub D, which was 2.911. And N is 8. The confidence level, it is 0.99. And just calculate. Negative 4.7666.7266, same answer. So you can get that right away by using your calculator. I have one more example here. So the table below shows the weights of 7 subjects. So let me bring it first. All right, let's go over this. So again, the table below shows the weight of 7 subjects before and after following a particular diet for 2 months. So we have that. Let's see what it says. Using a 0.01 level of significance test to claim that the diet is effective. Be very careful with this word. It doesn't say has an effect. In this case, it says is effective because we're going to write the claim differently for this problem. But let's double check. This diet is effective if I go for 1D or just for A. A lost weight. So if I take the difference and it lost 7 pounds. So, and 7 is positive. In this case, if the difference is positive, it's effective. Person D 180 was 183, after diet was 188. So gain weight. So it wasn't effective for person D. Same as person F. So 157 before, 159 after. So it wasn't, the diet was not effective for this person. Here, the diet is effective if the difference is positive. So be very careful. Now, if we write the claim, just look at one, it was effective. So the claim that we take mu sub d has to be greater than 0. If I can show that mu sub d is greater than 0, if this claim takes over, then we can say the diet is effective for the population, again with some significance level. So in this case, that's the claim you have to pick. Then you can find the critical value, which is just inverse t with your calculator. 0.01, it's right tail test. Do not divide it by 2 because it's only one tail. 0.016, you get negative 3.143, but it's a right tail test, so you take the positive one. The test statistics, you can use your calculator. So let's go ahead and use that. So again, the first thing you want to do is put all the differences in L1. Let me clear that. So our differences were 7 for the first one, 9 for the second one, 2 for the third one, negative 5, 14, negative 2, and 12. Now let's just go test this directly. So you can go to stat, test, and this is a t-test. Enter that. And here we're gonna go to data because we didn't calculate the mean and the standard deviation. Mu sub 0 is mu sub d, which is 0. L1 is fine because our data is in L1. And the test, it was a right tail test. You pick that and you just say calculate. So that's the claim, H1. In this case, T is 1.95, and we have the p-value also. And also here it gives you d bar and s sub d. So remember 1.95, and let's make the conclusion. So let me stop sharing that. So 1.95 is right here. It's in the non-shaded area. So the first claim failed to reject HO because it's in the non-shaded area. So we accept HO and we reject H1. And for HO, it was not effective. So we accept the claim that says it's not effective. Again, for most individuals in the sample, it was effective. And D bar was positive, so it was effective for the sample, but not effective for the population at a 0.01 significance level. So, and I put it, the diet is not effective. Or the right way of saying that, you can say we don't have enough evidence to support the claim that the diet is effective. So I think that's it for this lecture. You should be able to do the homework right now. Have a good one, everyone, and I'll see you in my next lecture.